Welcome to our first Perspectives interview as part of the new eBeam Initiative Fine Line Video Journal. I'm Jan Willis, and I'm the facilitator of the eBeam Initiative. And with me today, I have Hugh Durdan. He's the Vice President of Portfolio and Solutions Marketing at Xilinx. So welcome, Hugh.
Thanks, Jan. Pleasure to be here.
And one of the things about Hugh is that he's also our newest advisor to the initiative. And so I thought I'd have him start by just telling you a little bit about his background.
Sure, Jan. So I've been in the semiconductor industry a long time, probably too long, starting back in the early 80s at Digital Equipment doing 3-micron NMOS, believe it or not. But in terms of my more recent experience, today I'm at Xilinx, as you mentioned, and my responsibilities at Xilinx include the definition of our new products as well as the marketing for our tools and intellectual property course. And prior to Xilinx, I was at eSilicon, where I was Chief Operating Officer. And having manufacturing responsibility at eSilicon is really where I became aware of the eBeam initiative and the importance of what you're trying to do here. And now carrying forward with the definition of our new products at advanced process nodes at Xilinx.
Great. So you've mentioned your new products. So maybe you could tell us a little bit, especially about what your offering is at 20 nanometer. I know that Xilinx has had a reputation for many years as being one of the leaders at the most advanced nodes.
Yeah, so the FPGA industry in general is one of the first to move to the new process nodes. And the simple reason for that is that we've continued to benefit from Moore's Law. So the ability to get a higher performance, lower cost, lower power device at each successive process node has really driven FPGAs to be on the leading edge. So just last week, in fact, we announced some aspects of our 20 nanometer offering. One of those aspects is the fact that we believe that we're going to be the first to the 20 nanometer node in our business, and as well as the fact that we have already started to engage with some early customers. So compared to the industry in general, again, FPGAs and Xilinx specifically are continuing the trend of being one of the first to the new advanced process nodes.
Okay, great. Well, let me now kind of go back to some of your manufacturing experience and get your perspective on, sort of why and when has mass making become a critical issue for fabless companies?
Well, really, it's been at 20 nanometer. Of course, mass costs have continued to increase as we went through each successive node, both due to the complexity of making the mask and then just the number of masking layers as we add more metal and we add more complex features within the transistor. But the real critical tipping point at 20 nanometer was the fact that we had to go to double patterning. So for the critical layers on the device, we have to produce 2 masks because it's no longer possible to print them optically with a single mask. And so what we're experiencing and the implications of that are that if you go back to what we were doing in 28 nanometer, we've got about a 15% increase in the wafer cost just due to the fact that we now have to double pattern some of these critical layers.
Okay. So I think we all know that the industry has put a lot of money and time into EUV to try to address some of these challenges, but the fact is that it's still in development. In fact, a company like IBM was just saying very recently that they don't expect EUV to be production ready until the 7 nanometer node. So that leaves a pretty big gap between today and the future. What's your perspective on this gap, the challenges, potential solutions that you're looking at?
Well, it's very scary, quite honestly. There's a long way between where we are today at 20 nanometer and getting all the way to 7. Now, of course, a number of companies and foundries have announced the next generation beyond 20, some call it 16, some call it 14. And in general, the main advantage there is the transistor. Now, the thing that hasn't really changed between 20 nanometer and those process nodes is the metal interconnect. And for a company like Xilinx, our devices, in general, the die size is limited by the interconnect, not by the transistor pitch itself. So the implication, and there's been a number of publications about this, for instance, Handel-Jones with some curves that show the cost per transistor from process node to process node. And as you came down, we always enjoyed in the industry the fact that each successive node got less and less expensive to make a transistor. At 20 nanometer, it kind of flattened out, again, due to the double patterning. And if you look at 16, it actually starts to invert. which is going to be a real shock for the industry. And so what we need as an industry is a way to continue to allow us to shrink the metal interconnect and the device overall and improve the cost and get us back on the trend that we have historically had of lower cost per transistor for each node. Now, obviously we don't want to wait until 7 nanometer, which will be a number of years from now. We want something sooner than that. So some of the things that people are looking at is a hybrid approach, for instance, where they use optical lithography to print the wires, and then they use an eBeam technology to cut the wires. So rather than printing each individual wire, they print stripes, and then they cut the wires with eBeam. And that may be a way to fill this gap in between what we have today with optical lithography and while we wait for EUV.
Indeed, several of the eBeam initiative members have talked about this as complementary eBeam lithography, and there has been growing interest and growing number of companies working on this. Another topic that has really shown up a lot in the past year, and we've had a number of eBeam initiative members discussing their findings, is the changes in mask CD uniformity. There's a number of manufacturing issues that are causing mass CDU to be more negative. In fact, another section of this video journal is talking about some of those issues. And so the solutions, there's some ideas out there being discussed, but for a company like Xilinx, what's the implication of issues now with mass CDU?
So there's a number of implications for us. First of all, just put it in perspective, FPGAs, at least at the high end of the product offering, tend to be very, very large devices, close to what the reticle field can possibly image. And so for us, having consistency across the device is very important, because if we don't have consistency across the device, then we have to put in design margin to take into account the variability. And what design margin ultimately results in is an increased die size and higher cost. So especially in light of the fact that we have this dynamic where the cost per transistor is going up, design efficiency is very, very critical. So if we can achieve better uniformity and we don't have to put in the margining to deal with the variations, we can produce a more cost-effective product. Another way that it translates is yield. So an impact of lack of uniformity is lower yield. And again, lower yield translates to higher cost. And this is the worst time possible to have yield implications and have higher costs. So anything that we can do to increase the uniformity across the device will make our design easier, make our design more efficient, and make our yields higher, which ultimately will help to counteract these other trends that are driving the cost higher.
Okay. So given that there have been a number of findings demonstrating that this is an issue, what's your perspective on when does the industry need to be providing solutions for it?
So from Xilinx perspective, we're pretty much done with 20 nanometer. You know, we're going to tape out next quarter with our first device, and within an FPGA, devices we do a family of devices, so we'll do many, many more tape outs, but it will all be based on the same design elements. So our opportunity to adjust to future improvements in the process are limited. So for us, it would be the next generation process node, either 16 or 14. I think it's important to do it there because, again, that's the point where the cost inversion is going to happen. So to counteract that, we really critically need something. It could be possible for other companies that aren't as quick to move to 20 nanometer that there could still be a benefit for them as well. Okay. So any emphasis on 20 nanometer, I think, would be a benefit to the industry, although for Xilinx specifically, it's a little bit too late.
Okay, great. No, that's very helpful perspective to help sort of the whole design chain with timing and expectations. So let's just wrap up the interview now and talk a little bit about the eBeam initiative. Sure. Last year we did our first survey and we found that the members do really appreciate having a community around this where they can network, discuss the trends, but also that they value the content and, you know, feedback from companies like yourself. since you're now one of our newest advisors, do you have any of your own observations and advice going forward for the initiative?
Well, even though I'm new to the advisory board, I have been participating, so I have an awareness of what you've been doing for the last few years. And the value that I found is really the networking. So the ability to get out and talk to my peers that are facing the same challenges and understand how they're dealing with them. And I think the value that the initiative can bring is by bringing that collective perspective to the supply chain, because each one of us individually has a limited voice. So we can all go talk to our specific supply chain and tell them our challenges and our needs, but having a forum like this, which can collect the requirements of a wide variety of partners and suppliers and try to drive a solution for the industry, is the biggest value that I think we can get.
That's great. Thank you so much, Hugh, for doing this interview with us.
Oh, you're welcome, Jen.
And thanks to the audience for listening, and hope to see you next time.